Okay, so today we will talk about how to use, let's see, change the color. I use how to construct a D module, which is a term that's thrown around all the time in the Langlands program. And actually, it stems from using a little bit of calculus, a little bit of linear algebra, so some derivatives knowledge and some vector space knowledge, and a little bit of algebra or modern algebra, knowing something about rings and fields to construct a D module. The D stands for derivative, differential operator, whatever you want to call it. Okay, so let's recap the rules to building a vector space. So kind of counted 12 of these. So recap 12 rules to build a vector space. Okay, cool. So suppose you have a set M of elements, okay, called the vectors. Okay. Now you have a field K of elements. Okay. These are called the scalars. Usually, very often, it's going to be either the real numbers or the real number field, or the complex numbers, the complex number field, etc. Okay. Now, all right. What else? Now you have to have an addition operation that's closed, meaning that between the vectors, meaning that if you have A vector and B vector in M, that it is the case that there exists an addition operation. I'm not going to use the plus sign, obviously, such that A plus B is still in M. Okay, so A plus B is equal to, let's say, obviously C, and C is a vector in M. Okay, cool. So that's the addition operation. There's also a multiplication operation. Okay, there also exists a multiplication operation, not between two vectors. Okay, between a scalar and a vector. Multiplication operation, use the star sign, such that C in K and A in M and C times A. Oh no. And C times A is equal to let's say B, where B is still in M. Okay, still in the sets. Okay, cool. Now the addition operation has to respect associativity. So A plus B plus C is equal to A plus B plus C. Okay, associative addition is respected. Okay, is true. Okay. The addition operation must also commute. So A plus B is equal to B plus A. So commutative addition is respected. Okay, respected as well. Okay. Now there's also a zero vector. A zero vector, call it ZV, exists such that ZV plus A is equal to A. Okay. For any vector A in M. Okay. Okay. Now every vector H also has an inverse. Every vector H has an additive inverse AH. So AH plus H is equal to, of course, H plus AH is equal to the zero vector. Okay, is equal to ZV. For any H, so every vector H in M. Okay, almost there. So multiplication also respects a I kind of want to say like a associative-like rule. So it's the case that A and B in K and A in M, and A times B, A times B times A is equal to A times B times A. I don't know why it's like that, but yeah. So like an associative, the multiplication operation respects the kind of associative rule. Okay. All right. Now, if U is the identity, if U is the identity element of the field K, then U times A is equal to A for all A vectors in M. Okay. Two more. So the distributive property holds for adding vectors. Okay. So C times A plus B is equal to C times A plus C times B, where C is a number in K, or a scalar in K, and A and B are in M. Okay, they're just vectors. Okay. Also, G plus H times A is equal to G times A plus H times A. Okay, for G and H in K and A in M. So this one here is the distributive property holds for adding vectors, and this one you would say that distributive property holds for adding scalars. Okay, cool. I probably should have said that you could have skipped all that if you were familiar with vector spaces already. Okay, cool. Now you can replace the field K or enlarge it with a ring Q. So, and replace slash upgrade slash enlarge, whatever you want to call it, K, the field K to a ring Q. Okay, now what is this ring Q? So this ring Q is made up of all linear combinations of x to the n and d n dxn. So it's made up of x0, x1, x2, etc., also made up of ddx, d d2 dx2. Okay, so a bunch of derivative operators as well. Okay, by linear combinations, how are you even combining them? So by linear combinations, we mean linear combinations using complex numbers. Okay, complex numbers. Okay. Now you're probably gonna, now obviously x to the 0 is also in Q, and so is d0 dx0, which is of course just nothing. It's just not even a derivative. Just nothing stays the same. So you probably will notice after a little bit that, wait a minute, K. Well, if K is the complex number field, then K is just a subset or subring, or whatever you call it, of Q. Okay, K is inside of Q. Q contains all of K. If K was the complex number field. Okay. Now, Q has a name. Q is called the Weil algebra. Okay. And if you did replace K with Q, then the previous vector space is now called a D module. And that's it. Okay, it's now called a D module. Sometimes people call this called a module over the linear differential operators of one variable. So sometimes people say that we say that M is acted on by Q. Okay, we could have also said that M was acted on, okay, by K, but the action is kind of trivial because when an element of K is attached to an element of M, right? So that's a number attached to a vector. That's just scaling the vector. So it's kind of a trivial, nothing like crazy interesting that happens. Just kind of a stretching an arrow is kind of trivial or not that interesting. Just scaling / stretching. Okay. Cool. So I'll just leave you with this, which is that if you replace a vector, any vector spaces field with a ring, then in general you get a module. Okay, in general you get a module. If you replace it with Q, the Weil algebra, then you get a D module. Okay. Now just know that what happens. So some of the 12 rules will be broken. Okay. Can you tell which ones? Question mark. For hint, one hint is that rings are not commutative, or they don't need to be, or do not need to be commutative. Okay. And yeah, that is how you construct a D module.